Welcome to this final video in the Part A lecture notebook for the Computational Application 04 module in Math 1376. In this part of the notebook, we will be discussing iterative methods. Iterative methods and root finding methods, finding problems, generally refer to approaches that require a single initial guess of the root instead of an initial interval or set containing the root, like a bracketing method. These methods generally rely on defining what is called an auxiliary function, meaning an approximation to the function that is constructed at the current guess in order to form the next best guess at the root of the true function. Now, you might think that this is completely ridiculous. Weren't the above methods iterative? In a technical sense, yes, because they implemented loops. In fact, the false position method somewhat hints at the basic idea of these methods and looks similar to the secant method. The difference is that bracketing methods also require a description of a set that contains the root you are looking for, which is significantly more information to specify at the start of a problem than just a single initial guess at the root. One of the things you will need to consider, and which the instructions for the previous activity above hints at, is why some methods may be preferred to others in various scenarios. Now, the secant method is really an approximation to what is called Newton's method. It actually requires two initial guesses to the root. But the advantage is that neither of the initial guesses have to really even be that close to the root. Well, they kind of have to be close to the root, but they don't have to bracket the root. So this is best explained, I believe, in an interactive demo and playing what is hopefully this video that you're watching now. This wiki article you can click on actually includes some Python code on this simple example, which I copy and pasted below for the demo. Here are some good questions to keep in mind. Can you see where this code can immediately have some difficulty? What would be a good initial check to ensure that the code does not crash? Should a similar check be done at the end of each iteration? So let's go through this. Here's the secant method. It's rather short. We're going to pass a function f and then an x0 and an x1. This is kind of like the a and b, so it's 2 points that we saw before, except now neither one has to be, they can both, f of x0 and f of x1 can have the same sign. That's the difference. They don't have to bracket the root. And n is, again, the number of iterations. So what this is doing, if you look at what is it constructing when it loops through and it says x2 is equal to this formula right here. This is nothing more than the root of the line that goes through the points x0, f of x0, and x1, f of x1. At this point, I'll click on this link, and I'll show you what's going on here with this figure. So imagine that x0 was here, and there's f of x0. And x1 was here, and here's f of x1. If you drew the line through those 2 points, right, that interpolates those 2 points, and found where that line is equal to 0, that would be your next guess. Now, as it turns out, x0 and x1 here do bracket the root, which is at this point in the middle. However, notice that x1 and x2, which become the new guesses, this is x1 gets treated like the new x0, and x2 gets treated like the new x1 at the first iteration. At those 2 points, you form a new line, and you say, you know, the root is clearly not between those two because they both of the function values have the same sign. So you take the line through those 2 points, and then you get another point, x3. That is the root of that line. And then you would treat x3 and x2 like the new x0 and x1, and then you would find another line, and you would bisect, or not bisect, you would find the root of that line, and then that would form the new guess. And in so doing, you're going to iteratively refine your guess of the root in terms of the root of the lines that you're forming, which is very much like false position, except the points may or may not may or may not bracket where the root is, as was illustrated by this plot. And I've just coded up this method that's shown here, and they show the derivation of the method. It's actually quite short. And then, of course, there's this code that was, you can see, copy and pasted some nice Python code here. So one of the things you have to look at is you're dividing by a difference in function values, and you could potentially divide by 0. How could that happen? Well, someone could, like a user that doesn't know any better, just provide x0 and x1 to be the same point. That would cause this method to crash, and it's a good idea to incorporate a check for that, but that's something I'm asking you to do in an activity. So I'm going to run that, but then in this method, one of the things I'm going to do is I'm going to keep track of all the points that are generated in a list that I keep appending. So that's all I'm doing with this for the purposes of demoing this method, is I'm just creating a list of my initial points and then the list of function values, and I'm appending to those lists the roots of the next lines that we're finding to get our next estimate of the root. And when I do that, and I create a plot secant function, which was inspired by the plot bisection function that we saw at the earlier part of this notebook, I call the method, and everything else is about annotations. And these annotations are about creating lines that are the different secant lines and the roots of those lines. So I'm just going to run this. It's a lot of, again, code, but it's code involving plotting. So I just have to set up and plot all the different lines. So this is a good activity for you to go through and annotate and remark about what's going on in the various parts of this code. But when I actually look at what this is, it's quite nice. So when I run interact, that's kind of a big plot. So I think I'll just go ahead and make it a little bit smaller. Let's go, where's that figure? So I had 15 and 17.5. We'll make this more like, let's say 8 and 5. I'll make that a little smaller so it's easier to see. So that was the figure size. Let me rerun this. Let me run interact. There we go. So you can see here's x naught. I have my annotations. Here's x1. And then here's this line that connects those 2 points. And again, this is that same cubic function I keep showing throughout this notebook. And the root of that line is x2. Now, x1 and x2 are treated like the x0 and x1 points in the next iteration. So if I go to n equals 2, I don't want to necessarily clear the plot. There's x1 and x2, and now here's the line connecting the two function values, and where it passes through 0 is x3. That's the next guess of the root. If I go to n equals 3, then you see x3 and x2. These are the next 2 points. It's always the last 2 points are treated like the new x0 and x1 values. And you see the line that goes through these. I can hopefully zoom in and it doesn't disappear. Sometimes with these annotations it doesn't work. There we go. So here's x2, here's x3. So this is treated like x0, x1. There's the line that goes through those two function values, and that's where the line is equal to 0, and that's the x4 value right there. And then if I go to n equals 4 and I run interact, so it zooms out when I do that, but I can zoom right back in. And you can see x4 and x3 are like the new x0 and x1. And then here's the function value associated with x4. Here's the function value associated with x3. There's the line connecting them. And you see x5 is now a point that's getting closer to where the root is. Okay. And so I can, of course, go to like 6, zoom out. It's converging. Now the plot's getting a little messy, but it illustrates the point of what this method's doing. Now, all that I've done here is collect all of this into a secant class inspired by what we did with the bisection class. Notice below that we use a tall underscore f as a new parameter that was not previously considered with the secant method functions above. What we're doing is just like with the bisection. If the evaluation of the function at the point is close enough to 0, we're just going to abandon the algorithm. So you want to pay attention to where this is used in the compute secant method inside the class. So I'll just show you. If we find that the absolute value of this most recent function value that we've appended to this list is an absolute value less than its tolerance, so it's close to 0, we break out of this for loop and we're done. And then we just check what the I value was and set that was how many iterations we had, because we need that for any of our plotting tools that we want to use. Okay, I scrolled too far, sorry. So this just adds a little bit more sophistication to the algorithm, in that we may break out of the algorithm earlier if the current approximation to the root produces a function value that is of sufficiently small magnitude, meaning close enough to 0. As usual, I suggest you add doc strings and code comments below, but you'll notice that a lot of this looks very similar to what we saw with the bisection, except now I'm calling the parameters, the data attributes self.x0 and self.x1. I'm not using a and b because they mean something fundamentally different than the a and b that defined an interval for bracketing. The x0 and x1 are just intended for us to create a line that is approximating the function, and we find the root of that line, and then we just iterate from there. And so the rest of this is going to look very similar to the bisection algorithm, so I'm not going in terms of the structure of the class, so I'm not going to dwell on it. But I will point out that I already put in plotting capabilities that are based on the plot secant function I was showing above, which is similar to where we left the bisection class. in the first part of, or the earlier part of this notebook. So when you run this, and then you create a, let's say, a lambda function, and you create some secant object based on that lambda function, and you set some parameters like x0, 0.5, x12, and n is 10. Then when I look at that secant algorithm, and I plot it with n equals 3, you can see the iterations for it. If you don't like how crowded the plot is, you might think about editing it the way I was editing plotting with the bisection in order to clear the figure. So, and maybe you only want to plot the final secant line. Maybe you want to plot x0, x1, and then just the final 3 values, whatever the final interval value was, and then the root, or not interval, the final kind of x, 2x values, and then the root of the line connecting the function values associated with those. It's a good activity for you to try. Make your own class and try to edit the plot method for that. So I also show with the widget again how once I've created the object, I can access its plot secant method and interact with it this way with the widget. But I've already shown this with the bisection, so I'm not going to dwell it in here. And that's really the last part of this lecture notebook. Everything else is activities after this, and I will create some solution videos for the coding parts of those. Thanks for listening.